All right, as you can see from the board, today we're going to cover the binomial theorem, section 12.5, the binomial theorem. What do we do with the binomial theorem? Well, the binomial theorem is a theorem that allows us to expand binomials. I know that sounds almost like a pun, but that's the purpose of the binomial theorem. We learned about the binomial theorem back in Algebra 2. We learned the binomial theorem in Algebra 2. And then many of us might have forgotten the binomial theorem because we haven't seen it in quite a while. So today we're going to revisit the binomial theorem. Before we can visit the binomial theorem, we want to at least make an attempt to justify why does one need the binomial theorem. For example, what does the binomial theorem do? Well, clearly it must work with binomials. And so what the binomial theorem does is it helps us expand binomials. Now, if we have x plus a to the first power, we don't need any help expanding them. We know that's x plus a. If somebody asks us to find x plus a squared, we really don't need any help with that either. We know from experience, from algebra experience, that's going to be x squared plus 2ax plus a squared. And if they want us to find x plus a cubed, we actually have a formula that we learned in Algebra 1 for that, right? The cube of a sum, we know that formula. Some of us remember it using SOAP. Some of us remember it using just, well, Pascal's triangle, which we're going to talk about down here in just a second. But we know this is x cubed plus 3ax squared plus 3a squared x plus a cubed. Those three we typically remember, right? We remember those. The problem becomes what happens if somebody were to ask us to do something like, x plus a to the 7th. What happens if they ask us to find that? Well, that is not something that you and I want to have to FOIL out. I don't want to multiply this out, use the distributive property 6 times to find x plus a to the 7th. And there are times in a calculus class where we have to expand things like this. And if we have to expand this, we would want a better solution than, hey, just take x plus a, multiply it together 7 times. Because what happens if instead of 7, this is 71, right? There's got to be a better way. So we're going to do some work to justify, give us some background, so we can get to the theorem that's going to tell us how to find this in a much shorter manner than to take x plus a and to multiply it together 70 times, right? So let's think back to some of the things that we saw back in Algebra 2 that were related to the binomial theorem. One of the things that we saw back then was Pascal's triangle. And if you don't remember Pascal's triangle, you're going to remember it as soon as I start to write it down. Pascal's triangle went something like this. We write a 1, and then a 1, and then a 1, and then we write a 1. We add these two together and get a 2, and then we get a 1. Pascal's triangle has 1 on the outside. So again, this row is going to be 1. We add these together, that's 3. We add these two terms together up above, the row above, that's going to be 3. And then we close with a 1. And we can keep doing this. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then we close with a 1. And then we'll do one more row. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is also 10. 4 plus 1 is 5. And then we close with a 1. Now, what are these, right? Other than this cute little number addition game that we use to build Pascal's triangle, what do these represent? Well, these actually represent the coefficients of a plus x to the 0. This represents the coefficients of a plus x to the first, because what are the coefficients there? The first coefficient is a 1. The second coefficient is also a 1. This, if we continue our pattern here, this is a plus x squared. And we have it written here, but we'll write it over here again. We have 1a squared plus 2ax plus 1a squared. And if we look at the coefficients, right, if we look at the coefficients, they match Pascal's triangle. Pascal's triangle is a quick and easy way for us to find the coefficients on the first few binomial expansions. This is going to be a plus x cubed. And we wrote it up here, but we know what this looks like, right? This is 1a cubed plus 3 a squared x plus 3 ax squared plus 1x cubed, right? And I don't know why I made that an a. That's supposed to be an x, isn't it? And this right here, of course, then must be a plus x to the fourth. Reading my coefficients from Pascal's triangle, I get 1a to the fourth plus 4. And if you've noticed, what have I been doing up here? My powers on a started at 3 because that's my first term and I cube it, I get a cubed. And then my power on a went from 2 to 1 to 0. Whereas my power on x went from 0 to 1, right? There's a 1 there, to 2 to 3. So we count down the powers of a and we increase the power of x. Now my next coefficient would be 6. That would be a squared, right? a4, a to the third, a to the second, x to the 0, x to the first, x to the second, plus my next coefficient would be 4. And I would have a is going down, so that's a to the first, x is going up, so that's x cubed, and then I have a plus 1 x to the fourth, all right? So if we were asked to find a plus x to the seventh, we could use Pascal's triangle. It would take a bit of time to write all the rows down, but if we were asked to find x plus a to the 71st, using Pascal's triangle would be very inefficient. We would have to write down 72 rows of Pascal's triangle before we could get to the answer. And we need something better than that, right? We need something more efficient, something that's not going to take that much time. Now, an interesting thing about binomial expansions. Let's take a look here at some. We know where the coefficients come from, right? We've talked about that. Let's look at another characteristic. This is a to the first. This is, so a cubed, then a squared, then a to the first, then a to the 0. A to the fourth, a cubed, a to the second, a to the first, a to the 0. Now, we don't write the a to the 0 down here, but we could, right? We could write the a to the 0 there. It's there. What's an interesting observation that you can make about the exponents, right? Now, remember what this equaled. This equaled 1. What's an interesting observation about the exponents? This is a 1 and a 1, isn't it? This is a 1 and a 1. Let's take a look at our exponents. What do we get when we add 4 and the x to the 0? 4 plus 0. I'm just talking about the exponents now. 4 plus 0, that would be my exponents. Those add to 4. What about these exponents? 3 plus 1, also 4. 2 plus 2, 4. 1 plus 3, 4. 4 plus 0, 4 again. Does it work that way up here on the a plus x cubed? Well, let's see. We have an x to the 0. It's not there, but there's an x to the 0 right there. 3 plus 0, 3. 2 plus 1, 3. 1 plus 2, 3. 3 plus, it's not written. We'll put it here. We have an a to the 0 here. 3 plus 0, 3. So one of the things that you and I can pay attention to when we're doing these binomial expansions is we can pay attention to this characteristic. Our exponents are always going to add up to be our power. So one thing we know about this, right? One thing we know about this. Well, for example, all of us know the first term is going to be x to the 71st. And all of us know the last term is going to be a to the 71st. Now, we don't know a lot of information about the terms that come in the middle. And what do I mean we don't know a lot of information? Well, what I mean is we don't know the coefficients. We know this coefficient is 1 because that's what Pascal's triangle always starts with. We know this coefficient is 1 because that's what Pascal's triangle always ends with. But we don't know the coefficient of the next term. We have no idea what the coefficient of the next term is. Now, if you're thinking to yourself, but I know something about the next term, you're correct. You do know something about the next term. You know the power on x, and you know the power on a. Because you know from your observation down here where we did this in red, you know that x goes down by 1 and a goes up by 1. And we also know that they have to add to 71. So we know the exponents. Now, for the next term, we don't know the coefficient, but we do know the exponents. X goes down by 1, a goes up by 1. For the next term, again, we don't know the coefficient, but we can keep doing this, right? We have this pattern that we can follow. We know every time we write down one of these terms, their exponents have to add to 71, don't they? This adds to 71, this adds to 71, this adds to 71. Now, how does this tie into our sequences and series game? Well, that's a great question. We could number these terms. We could say this is the first term and the second term and the third term and the fourth term. Right? We could do that. We could do that. So we're going to try with the binomial theorem to come up with a way, since we already know how the exponents behave, we know how they behave, we're going to try to come up with a way to answer the question of what goes here, and what goes here, and what goes here. That's what the binomial theorem is going to help us find. Now, we could get there by using Pascal's triangle, but Pascal's triangle is not efficient, right? It's not efficient. So we need a better way, and that better way is going to be the binomial theorem. So, we've reviewed Pascal's triangle. We see how Pascal's triangle tells us the coefficients. For the first few binomial expansions, that's going to be useful. Right? That's pretty useful. In fact, if you asked me to find a plus x to the fifth, I can honestly tell you that I may not use the binomial theorem. I just may, on a piece of scratch paper, write down Pascal's triangle and use this row right here to find a plus x to the fifth. It's probably going to be more efficient for a plus x to the fifth to use Pascal's triangle than it would be to use the binomial theorem. But when we get past that, past the fifth power onto the sixth or the seventh or even the 71st power, Pascal's triangle is going to become very inefficient. All right. So we've reviewed Pascal's triangle. We're going to put that away. We're not going to forget about it. We're going to put it away. We know when to use it. We can use it on small powers. 2, 3, 4, 5, right? And now we're going to talk about what else do we need, right? What else do we need to remember from last year's Algebra 2 journey before we can actually write down the binomial theorem, right? We need a little bit more review of things that we've seen, but we may have forgotten. Okay? So Pascal's triangle, item number 1. Right? Item number 1. What's something else that we can use or that we need to remember from last year? Right? Last year, we learned about a mathematical counting principle called combinations. All right, combinations. That's hard to see, isn't it? So I'm going to put that color away. We won't use that one anymore. So we learned about something called a combination. It came with its own symbol, a symbol that we had not encountered before, a symbol that looked like this. And it was difficult when we were writing this down for the first time. A lot of us, when we write combinations down for the first few times when we're learning them, we always put a fraction bar in there, and then we think to ourselves, oh, that doesn't belong there, then we have to go back and erase it. So make sure you remember, this isn't a fraction, it's not n divided by j. What does this mean, right? What does this mean? This, if we had to read this out loud, we would say this expression, this mathematical expression is the number of ways we can choose j objects from a group of n objects. So let's see if we can try to explain this in a way that's a little clearer than this, right? What does it mean if somebody writes, right? If somebody writes something like 3 choose 1. What does this mean? What does this mean? Now there's a mathematical expression, and we'll get to that. We'll get to that. But before we do the mathematical expression, we need to understand what they're asking us to do. So what they're saying here is you have three objects. Okay? Now maybe those objects are just, you've got a you have a bag, and in that bag there are 3 balls. Right? There's a green ball, there's a blue ball, and there's a red ball. Okay. So you have 3 balls in a bag. And the question is, so you have 3 objects, the question is, how many ways can you choose 1 ball? How many ways can you choose 1 ball? Well, you can reach in your bag, right? You can reach in the bag, and you could pull out a green ball. That would be one thing that could happen. Now you're only allowed to choose 1, so you could reach in the bag and you could pick 1 green ball. So that's our first outcome. What else could happen? Well, you could reach in the bag, right? You could reach in the bag and you could choose the blue ball. That's a different outcome. Or you could reach in the bag and you could choose the red ball. Again, a different outcome. The question is asking, how many ways could you do this? What's the total? Now, is there anything else we could do? We could reach in the bag. We have to choose 1 ball. We could have chosen green. We could have chosen blue. We could have chosen red. That's all. That's all we have. So the answer to this question is 3 ways. Or 3 outcomes is how we would phrase that in a statistics class. 3 outcomes. Okay. Now, what would it happen? We'll use the same bag. What would happen if we had the same bag with 3 objects in it, and we wanted to reach in and we wanted to choose 2 objects? 2 objects, right? We can read this as you have 3 objects. How many ways can you choose 2 balls? Right? That's what this says. 3 balls in the bag. How many ways choose? Two balls. All right, so what's one possible outcome? Well, you could reach in the bag and you could take out a green ball. And now you got to choose two balls. You've got the green ball in your hand, but you got to choose another ball. So since you have the green ball in your hand, you can't choose another green ball. There's only one green ball in the bag. So you could have picked, let's just say, you could have picked the red ball. Right? That's an outcome. That could have happened. Green ball, red ball. Are there any other possibilities? Well, of course there are. You could have picked the green ball, couldn't you? You could have picked the green ball. But with the green ball, you could have chosen which ball? You could have chosen the blue ball, correct, the blue ball. All right. Are there any other outcomes? Well, perhaps the first ball you picked was blue, right? We haven't taken that into account. Let's say the first ball we picked was blue. So now what happens? We reach in the bag for our second ball, right? We've got the blue ball in our hand. We reach in the bag for our second ball. We pull the green ball out. We've already got that. Green, red. We already have, we pull the green ball out. We've already got that. Green, blue. We've already got that. That's done. We counted that one. So that doesn't count on our list, right? That doesn't count. How many ways can you choose two balls? Doesn't mean how many ways can you choose any two balls. It means how many ways can you choose two different balls in each of your outcomes. Well, we chose blue. My second ball is green. Okay, that doesn't count. I already have that. So what else could I have gotten? You're right. I could have gotten the blue ball, and my next ball could be red. Okay, could be red. Now, is there another possible outcome? We've already counted choosing the green ball first. We want to follow a pattern here if we can to make this as easy as possible. We already chose, we took the green ball out, and we got red and blue. Now we chose the blue ball first. And then we said, okay, I chose the green ball second, but I already had that, so I put the green ball back, and I chose the red ball. That's a different outcome, blue, red, that's okay. What happens if we choose the red ball first? All right, is that going to generate any new outcomes if I choose the red ball first? Well, if I choose the red ball first, I could choose the green ball, but I already have that. Red, green, I already have that. I could choose the blue ball, but I have that. Blue, red, I have that. I already have that. So that's not going to give me a distinct new outcome. So the answer here is going to be three ways. Or three outcomes. Now, before you get the idea that it's always going to be three, let's do one more example. Right? Let's do one more example. Let's add a fourth ball to our bag. We'll add a purple ball. Okay. So now we have four balls. Right? We have four balls. So how many ways? Right? So now we have four balls. And let's ask ourselves, how many ways can we choose two balls? All right, so now we have four balls in the bag. And we're asking, how many ways can you choose two balls? Now stay with me here. There's a purpose to this. This is going to get us someplace. I promise. This is not just a waste of our time. Well, what could happen? We're trying to choose two balls. Now remember, we want to follow a pattern. Let's again say we picked the green ball first. Okay, out comes the green ball. Who could we have chosen along with the green ball? Well, what other ball could we? You're right. We could have picked the blue ball with the green ball, right? Okay, that's one outcome. Could we have gotten a different combination? Combination. It's the first time we've used that word. We're going to get to that word in a second. Could we have gotten a different combination? Yeah, we could have taken the green ball out, and instead of the blue ball, we could have gotten the red ball. That's a different combination. Is there a third combination? Well, you're right. We could have taken the green ball out, and with the green ball, we could have gotten the purple ball. Now, is anything else possible choosing the green ball first? And the answer is no. We have all the possible outcomes right there. But where do we go next? Well, let's change it up. Let's do what we did up here. Instead of choosing the green ball first, let's choose the blue ball first. All right? Well, who could have come out as my second ball if I chose the blue ball first? If I take the blue ball out, I don't want to get the green ball. I already have that over here. But I could have gotten the blue ball and the red ball. Anything else possible? Is there another combination that's possible? You're right. I could have taken the blue ball out first. And with the blue ball, we would have picked what would be different. We have blue and green here. We have blue and red here. So we could have had blue and purple, huh? Are there any more opportunities? I think there are. We could have taken, instead of the green ball first or the blue ball first, we could have taken the red ball first, couldn't we? Now, what happens if I pull red ball first, then green ball? Well, we've got that. That's B. We've got that one. What happens if I pull red ball first and then blue ball? I've got that one here. So what's the only combination we're missing with the red ball? The only combination we're missing is red and purple, isn't it? Red and purple. Now, is there another option, right? Is there another opportunity? Is there a seventh outcome? And I'm going to tell you right now, I don't think there is. We've chosen all the options with green first. We've chosen all the options with blue first. With red first, we only ended up with one. What happens if we draw purple first? Right? Well, we already have purple and green. We already have purple and blue, and we already have purple and red. So this is not going to be a new outcome. So how many ways could we have achieved this? Right? What's our answer here? Our answer is 6 ways or 6 outcomes. All right. Now, I promised you that this was going to get us somewhere, right? Someplace. So let's keep this in mind. 6 ways. And let's clear some space here. Clear some space. And let's ask ourselves a few questions about 4 objects. Let's ask ourselves, what's this mean? 4 objects, choose none. Right? 4 objects, choose none. That's what that means. We can write this in shorthand as 4 objects, choose 0, right? Now, how many ways can we do that? How many ways can we reach our hand in the bag and pull our hand out with nothing in it? 1. There's actually an answer to this. You can put your hand in the bag and you take your hand out. There's actually a solution to this. It's one way. There's only one way to do that. What about 4 choose 1? So we have 4 objects. We want to choose 1. Hey, there's an E in there, isn't it? Choose 1. Well, how many options are there here? How many options are there? We could have chosen the blue ball. My blue pen is dying. All right, we could have chosen the blue ball. I'll grab a different blue pen. There we go. That's an option. What else could have happened? We could have chosen the purple ball. Now remember, we're only allowed to choose 1, right? We're only allowed to choose 1 ball here. We could have chosen the green ball. And you're right, we could have chosen the red ball. So that would have given us 4 ways. All right, 4 ways. Now we've got 4 choose 0, we got 1. 4 choose 1, we got 4. 4 choose 2, we've got 6. Those numbers seem familiar to me. I'm going to keep going. What's 4 choose 3? Right? What does this mean? It means we have 4 objects. We want to choose, I remember D, 3. Well, let's just write these down. What could this look like, right? If we had 4 objects and we wanted to choose 3. We could get, right? We've been starting with green, so we'll go ahead and start with green. We could have gotten, right? When we chose 3, we could have gotten green. Then we could have gotten blue. Now we get to choose 3, right? Green, then blue, and then we could have gotten purple. Now is that all that can happen? Well, no. We could have gotten green. We could have gotten blue. And instead of purple, along with that, we could have chosen red. All right? Now, what other options do we have? Well, we could have chosen, right? We could have chosen green first. But instead of choosing blue second, let's say we chose red second. Who could we have chosen third, right? Who could we have chosen third? Well, could we have chosen blue third? No, we have green, red, blue right here. Maybe this purple pin is a hint, right? We could have chosen, green, then red second, and we could have chosen purple third. Now, are there any other options where we could have opened up with green? And if you're thinking, well, yes, we could have chosen green, and then we could have chosen purple second. Okay. Who's going to come third now? What balls are left in the bag? There's a blue ball left in the bag. Well, green, blue, purple is right there. We've already got it. Okay. There's a red ball left in the bag. You're correct. But we've got green, red, purple right there. So we have exhausted what we could do by picking green first. So who could we now pick first? Well, we'll pick blue first. All right. Who are we going to pick second? Well, if we pick green, we've already done blue-green up here. So green is out, right? Green is out. We'll say we chose red as our second ball. Well, who can be our third ball? Green. So that would be blue, red, green. Well, that's right here in row 2. Blue, red, green. That's out. How about purple? You're correct. We don't have that one yet, so we could have chosen purple for our third ball. Are there any other combinations? Well, we tried blue, red, green was out. We did blue, red, purple. That was good. What happens if we choose red first, right? What happens if we say, I'm going to choose red first? Well, and red, purple, green. Red, purple, green. Is that an option? Yeah, it is, but we have it right here. How about red, purple, blue? Well, that one's right there. Okay, so purple for the second ball is not a good option. How about blue? Red, blue, purple, here. Red, blue, green. Red, blue, green is here. So blue is not a good option there. Let's try green. Red, green, purple. Well, red, green, purple is here. Green, red, green, blue. Red, green, blue. Do we have red, green, blue? Yeah, we do, right here. So if we start with red as our first ball, there are no other options. The same thing happens with purple. There are no other options. There are 4 ways here. 4 ways. Now these numbers are starting to look really familiar. 1, 4, 6, 4. What happens if we have 4 choose 4? How many ways can we put 4 objects in the bag and choose 4 of them? Well, there's only one way, right? There's only one way that could happen. We reach in the bag and with our hand, we grab all 4 balls. There's only one way that could happen. We pull out the purple ball, the red ball, the green ball, and the blue ball all at the same time, right? Because we have to choose 4. So there is only one way, right? One way this can happen. Now, I think these numbers, they might remind us of something. Look at this. We have 1, 4, 6, 4, 1. If we just write these numbers down here, 1, 4, 6, 4, 1. That's the number, the possible solutions to the question, how many ways can I put 4 objects in a bag and pull them out? Either one at a time, none of them, 2 at a time, 3 of them at a time, or all 4 of them at a time. And you know a funny thing? These numbers are not original to this little video we're doing here, huh? We've written these numbers down once before. These numbers come from Pascal's triangle. So these combinations, they lead us to the numbers in Pascal's triangle. And that's our quest, right? That's our quest. That's our quest during this binomial theorem journey, is to ask ourselves, how do I find these coefficients? Where do these coefficients come from? Well, they actually come from these combinations. And that's why when we wrote down the binomial theorem last year in Algebra 2, there was an n choose k, or an n choose m, or an n choose j part to the binomial theorem. And many of us were confused by that. So hopefully we can at least get a little bit of a real world perspective using our box or our bag with balls in it. This is where the binomial. So if I had to ask you, right? If I had to ask you about a plus x to the 71st, I would just put 71 distinct balls in the bag and I could play this game. It would take an awful lot of time and I could generate these numbers. However, that's not efficient. That's going to take a lot of time. So what I'm hoping is that we can find some way to write these numbers down a little quicker than actually putting balls in a bag and pulling the balls out and writing down all of our possible outcomes. And that is the next thing we're going to talk about. How can I compute these combinations in a more efficient manner? Because what we're doing right now works. It works. But if we're going to sit here and ask ourselves, all right, I have 22 balls in the bag. How many ways can I pick 15 balls out of that bag? That is a very confusing question. A very confusing question. And fortunately for us, right? Fortunately for us, there is a mathematical definition that tells us how to calculate n choose j. And that definition involves our good friend, the factorial. The answer to this, we can do it by putting balls in a bag, but that is going to take a lot of time. The answer to this is n factorial divided by j factorial times n minus j factorial. Now let's test that, right? Let's test that. You and I just did 4 choose 2. And we know from our previous example the answer was 6. Let's see if indeed the answer works out to be 6 with our formula. So if we were going to use this formula, we would write this as 4 factorial divided by j is 2, so that's going to be 2 factorial. And then this would be 4 minus 2. Now remember, the factorial goes on the outside, not n factorial minus j factorial. So what does this look like? Well, this looks like 4 times 3 times 2 times 1. This looks like 2 times 1 times 4 minus 2 is 2, right? So that's 2 factorial. So that's another 2 times 1. And now we're going to cancel. 2 times 2 is 4. And what are we left with? On the top, we're left with 6. On the bottom, we're left with 1. And we get 6. All right? So when we Now, our calculators are fine for choose 2, right? I don't know what brand of calculator you have, so I'm not going to go through the steps of how to find that on your calculator. You can look at the instruction manual that came with your calculator or Google how to use your calculator and define combinations. But I do want to show you a little bit of factorial math just to make this easier in case you're going to do it by hand. Now, if we're going to get into big numbers like 25 choose 16, we're going to have to use a calculator to do this. Otherwise, you and I are going to be here for hours and hours and hours trying to write this down. What does this look like, right? This is 25 factorial divided by 16 factorial times 25 minus 16 factorial. All right, that's using our formula here. N is 25, J is 16. Now, what does that look like? That looks like 25 factorial divided by 16 factorial. And what's 25 minus 16? That's 9, right? So let's just write that. Times 9 factorial. Now I'm going to show you a little trick. It saves some time if you have to do this by hand. This is not something we want to do by hand, but if you had to do this by hand, right? If you had to do this by hand, what do we know this is? This is 25. That's what it is on the top, isn't it? What do we have on the bottom? We have 60 times 50 times all the way down to times 2 times 1, right? That's 16 factorial. And then we're multiplying that by 9 times 8 times 7 all the way down to 2 times 1. Now, here's the trick. Again, it's not a great trick, but it does help somewhat. Pick the bigger of these two and divide all of these up here. Now, if you think about it, this is 25, 24, 23, 22, 21, 20, 19, 18, 17, 16, 15, 14, 13, 12, right? Those numbers are all up here. In other words, I can cancel this with a whole bunch of numbers that were up here. Now, again, this is not great. This is not going to make this fabulous. What is going to be left? We're going to have 25, 24, 23, 22, 21, 20, 19, 18, and 17 is left, right? Because 16 on down canceled with this 16 factorial down here. Now, what do we still have on the bottom? On the bottom, we have 9, 8, 7, 6, 5, 4, 3, 2, 1. Now, again, I didn't promise you a miracle here. I didn't say this is going to work out fabulously. Now, where are you going to go from here? Well, you have a lot of choices. You could do things like this. 5 times 4 is 20, right? 2 times 9, 18. Now, where are we going to go next? Well, 3 times 6 is 18. We can't do that. 7 times 6 is 42. Those aren't going to work. So now we just start picking them off individually. We go, well, 3 goes into 21, leaves me 7. Right? What does 6 divide into? Well, 6, right? 6 will go into 24 and leave me 4. How about 7? Will 7 go into 25? No. 4? No. 23? No. 22? No. 19? No. 17? No. 7 does cancel this 7 right here. Look at that. Now what's left? Our friend 8, right? What are we going to do with 8? Well, we could divide this 4 into this 8 and get a 2. Then we could take that 2 and divide it in this 22 and get an 11. And now we have to bust out our calculator. Because now look what we have. We have 25 times 23, right? That's gone. Now we have an 11 right there. That 7 went away. 20's gone. We have a 19 and we have a 17. Now that's a really big number. I have no idea what that number is. I'm not going to grab a calculator and multiply that out. That's how many ways, if we had 25 balls in a bag, we could pick out a group of 16. There are a lot of opportunities there for that. That's a huge number, which is why most of the time when we do this kind of factorial work, we work these out with our calculator, right? Because, well, I mean, we could do this arithmetic, and it's kind of fun, canceling, it's kind of fun. And we get this, and now we only have 5 numbers to multiply in our calculator, so we could multiply those 5 numbers together. Or we could learn how to do the combination on our calculator, right? It's probably a much more efficient way to work this out. All right, where is all of this taking us, right? We've now met Pascal's triangle. We met our combination. How many ways can we choose j objects from a group of n of them? And we noticed that this actually ties into Pascal's triangle, doesn't it? This gets us our coefficients, right? This is, that's not a very good is the expression we will use to find our coefficients. That's it. N choose J. That's going to be the magic expression that allows us to find our coefficients. All right? So what am I going to do now? I'm going to erase this, and then we're going to get to the Pascal's triangle. Sorry, Pascal's triangle. We're going to get to the binomial theory. Okay? And once I write down the binomial theorem, we'll do some examples that look like the homework problems so that you can use those examples along with the examples that are in your textbook and any other videos you may want to watch online to find your way through the homework assignment on section 12.5. Okay. So let's write down the binomial theorem. Now, let's don't panic while we're writing it down. We're just going to write it down. It's going to look less nice than we would, particularly want it to look like. But here's what the binomial theorem says, right? It says, let x and a be real numbers. For any positive integer. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And we have, and then here it comes, right? We have this, x plus a to the nth power. If they wanted us to write this out, what is this going to look like? Well, it's going to look like n choose 0. There's our combination. That's going to be our coefficient, right? That's the connection that we just discovered. The combinations give us the numbers from Pascal's triangle. So we're going to start with n choose 0. We're going to have x to the n here. Right? This person gets that whole power. Now, it's not written in your book. I'm going to write it here, though. I'll write it in a different color. I'll write it in green so it's not very bright. There's going to be an a here, but it's going to have a power of 0. Okay? I like to write that in when I write down the binomial theorem, at least for the first time. Now, who's the next term going to be? Well, the next term is going to be n choose 1. Now, we know what happens. We know, we've learned this in Algebra 1 and Algebra 2. We know the power of this factor goes down by 1. And while that's happening, the power of the next factor goes up by 1. What's our next term going to be? Can you write it down? Go ahead, write it down. Well, I hope you wrote n choose 2, right? X. We're going to take away 1 from here, so that's going to be n minus 2. We're going to increase this by 1. That's going to be a squared. All right? Now, this keeps going and going and going. And somewhere in the middle, we're going to get n choose j. Now don't let this confuse you. It's going to be okay. So I can't write them all down because I don't know what I started with. I don't know if that's a 26, a 37, a 2008, or a 2. I don't know what that is. Somewhere in the middle, I'm going to get some general middle person. Who's my middle person? Well, my middle person is going to be, instead of n choose 0 or n choose 1 or n choose 2, we've counted up all the way to j now. That's what we're saying here, right? We're saying we've counted up to j. Now, if you take a look, I'm going to draw some arrows here. If you take a look, this number is the power on A. That is the power on A. So we know, I like to write the second one first. I like to write the second one first. I like to write my A, and then I know my power on that's going to be J, because that's the pattern that we've been following. Now, what's the power on X going to be? I always write this one second. I understand it comes first, but I write it second. What's the power on X going to be? Well, if you look right here, X has an N. Okay, that doesn't tell me a lot, but look what happens after that. This is a 1, N minus 1. This is a 2, N minus 2. Oh, wait a minute. This is a 0, N minus 0. So if this is a J, this is going to be N minus J. Now, if that was confusing, if right now you're thinking, ooh, I didn't get that. Okay, that's not a big deal. Push pause, back up 37 seconds, and listen to it again. And if that still doesn't make sense, push pause, back up 37 seconds, and listen to it again. And keep listening to it until it makes sense. This ends up being the power here. And then this power is this number minus this number every single time. Now, where does this eventually stop, right? Because it has to stop. It can't go on forever. Where does it stop? Well, we have 0 on the bottom, 1 on the bottom, 2 on the bottom. Now we're up to J. Eventually, right? Eventually, we're going to reach N. Now remember, my trick, my idea is I write this one's down first, right? That's the power that goes there. Now, who's the power here then? It's going to be this one minus this, N minus N, 0, right? So our last term, I'm going to leave it like that for now, but I'm going to leave it like that only while we talk about it. I'm going to clean it up. Our last term is going to look like this if we follow our pattern, right? If we follow our pattern. But we know x to the 0 is really not. We don't write that down. X to the 0 is 1. So our last term, it doesn't have an x, right? It doesn't have an x. So this is the binomial theorem. It's not here to confuse us. It's not here to worry us or to scare us, right? And because we're now competent at sigma notation, we can actually write this in sigma notation. We're going to say J starts at 0, right? This is our J down here, right? This is J. J starts at 0. J stops at N, right? Sum means to add. What do my coefficients look like? They look like N choose J, right? And then what are my powers? Well, let's write this one down first. This one's easier to write. A is going to have J for a power. And X is going to have N minus J for a power. Now, all the way back in the beginning of the video, when we were expanding, using Pascal's triangle, when we were expanding x plus a to the second, x plus a to the third, x plus a to the fourth. Go back and look at your notes. You have it written in your notes. I pointed something out to you. I pointed out to you that every time you write these down, They have to add to n. They have to add to this number right here. And if you look, every one of those combinations adds to n. If you add those up, n minus 1 plus 1, n. N minus 2 plus 2, n. N minus j plus j, n. That's a check that you need to remember when you're doing problems with the binomial expansion. Your powers always add up to n. All right? So where are we going to go from here? Well, let's look at some homework questions and ask ourselves, how do we apply this, right? So what does a typical homework problem look like? Right? What do they want me to do? Well, they have problems where it just says expand. Now, don't panic. They're not going to make this 75 and ask you to come up with 76 terms here. They're going to give you things, they're going to give you things like x plus 3 to the 5th. And they want you to write this out and fully simplify. Now, how are we going to do that? We're going to use this power. The power of this theorem right here. Our x is x, our a is 3. Our n is 5. Right? Now, if you need to jot that down over here, jot that down over here. Your x is x, right? Your x is x. Your a is going to be 3, and your n is going to be 5. If that's going to help, then jot that down. There's nothing wrong with that. Now, what is this going to look like? N is 5, so we're going to begin with 5, choose 0. The power that goes on 3 is going to be 0. I told you, I always write this one first. The power that goes on x is going to be this number right here minus this number. Or another way to think about it is these have to add to 5. So I've got to put a 5 there. Who's my next term going to be? It's going to be 5, choose 1. Now x goes down by 1. The power on 3 goes up by 1. Or this number matches this number, and this number is the difference of these two, right? That's what we said, n minus j. There's a pattern here, and once you do a few of the problems, then you become very comfortable with the pattern. Now we have 5, choose 2. X goes down, 3 goes up. 5, choose 3. X goes down, 3 goes up. Do these add to 5? Yes. 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 Okay, then we're doing things correctly. 5, choose 4. X goes down, 3 goes up. Still adds to 5. The exponents add to 5. 5, choose 5. X goes down, 3 goes up. Now, if all they wanted was that, it'd be a great homework problem. Unfortunately, we now have to do the arithmetic. Groaning's not going to solve it. We still have to do the arithmetic. How many ways can we put 5 objects in a bag and take out 9? We know the answer to that. The answer to that's 1. So this is going to be 1x to the 5th. How many ways can we put 5 objects in a bag and take out 1 object? We know the answer to that. The answer there is going to be 5. So this is going to be 5. Now that's also a coefficient, right? That's 3 to the 1st. So that's going to be 5 times 3x to the 4th. Don't forget to multiply this 3 by this 5. Now what about 5 times 5 choose 2? Well, we could do 5 choose 2 off to the side here, can't we? 5 choose 2. What's 5 choose 2? You know, that's 5 factorial divided by 2 factorial times 5 minus 2 factorial. That's 5 factorial divided by 2 factorial times 3 factorial. Now remember the trick? The factorial trick I taught you? If you don't, I'll do it again. We have 5 times 4 times 3 times 2 times 1. That's our numerator. On the bottom, we have 2 times 1 times 3 times 2 times 1. I said, and I'll say it again slowly, take the bigger number, cancel those out. The bigger number, cancel those out. Now what do we have? We have 20. 20 divided by 2, we get 10. So this is going to be 10 times 9. 3 squared is 9, x to the third. Now what about 5 choose 3? Well, 5 choose 3 is 5 factorial over 3 factorial, 2 factorial. And if you're thinking to yourself, hey, we just did that. Now where'd the 2 factorial come from? Maybe I shouldn't have skipped that step. That's going to be 5 minus 3 factorial, right? So that's going to be 5 factorial over 3 factorial, 2 factorial. Look, we just did that, right? We just did that. That number and this number are going to be the same. They're going to be the same. That's a characteristic about factorials that we're going to want to remember. 5 minus 2, 3. 5 minus 3, 2. Okay? Those are going to give us the same value. This is also going to be 10. We don't need to rework that. So this is going to be plus 10 times 3 cubed. That's 27. X squared. Have you noticed how I'm not multiplying these out as I go? I'm not multiplying them out as I go because I remember something about Pascal's triangle, and you know something about Pascal's triangle. These numbers go 1, 5, 10, 10, and now they count down, right? Don't they count down the same as they counted up? Isn't that how Pascal's triangle worked? Remember, we had a row that went 1, 4, 6, 4, 1. And the next row was 1, 5, 10, 10, 5, 1. That's a characteristic of Pascal's triangle. Once we've counted up, counting down, we don't have to do the work because the coefficients going down Pascal's triangle are going to be the same as the coefficients going up Pascal's triangle. What am I trying to say? I'm saying 5 factorial is going to be 5. Sorry. I'm saying 5 choose 4 is going to be 5. 5 choose 5 is going to be 1. So we already know that this is going to be a 5, right? From here. 3 to the 4th, that's 81. Right? That's 81. X plus 5 choose 5. We did that. How many ways can we put 5 objects in a bag and pull 5 objects out? 1. So that's going to be 1 times 3 to the 5th. Now 3 to the 5th is 3 times 81. That's 3, 2, 4, 243. So what is the final answer to this homework problem? X to the 5th plus 15x to the 4th plus 90x cubed plus 270x squared. 5 times 1 is 5. So that's 405 x's plus 243. Don't multiply these together as you go. You're going to lose the pattern and make your work much harder. So that's one type of problem they can ask us to work out. Pascal's triangle problems, they're kind of fun. I mean, they're just a bunch of arithmetic. It's like, can I do arithmetic? Can I follow a pattern? Can I do this without getting lost? And the answer to all those questions is yes. Yes, you can. So I'm going to erase this now. Right? If you have to go back and watch it again, go back and watch it again. Let's get this off here. And let's see, what's another kind of problem, another type of problem they may ask us to do in the homework. Right? Well, they have a lot of these questions. You probably remember these from Algebra 2, where it says, let's go ahead and fill that back in there, J equals 0. So there were a lot of questions like this in our Algebra 2 book. And it says, all right, what is the coefficient of x cubed in the expansion of 2x plus 1 to the 12th. All right? 2x plus 1 to the 12th. Now, they want to know, what's the coefficient of x cubed? Now, they do not expect us to write out all 13 terms. They don't want us to expand this. They don't want us to do this expansion right here for this, and then come all the way down here to the end and go, here's the x cubed, person, your coefficient is. That is inefficient and unnecessary. They want us to be able to organize our thoughts, organize our strategy, so that we can just do that term right there. Just that term. No other term. They don't want us to start the expansion of this. They don't want us to say, well, this is 12, choose 0, 2x, because in this game, my x is 2x, right? The person who comes first is 2x. My a is 1, and my n is 12. They don't want me to do this. They don't want me to say this is 2x to the 12th, and this is going to be 1 to the 0, plus 12, choose 1, 2x to the 11th, 1 to the 1st. If I were to do this on the test, the teacher would probably give me not very much credit, because I don't want, nor does your instructor want you to do all of this work to pick off one coefficient all the way down here at the end. They want us to show an understanding of the binomial theorem. They want us to say, okay, if I just think about this, I can figure out who x cubed is going to be. I can figure that out, because let's see if we can just take a quick look at what we've written down so far, right? And perhaps we can see it from here. The power here on x is going to be 12. The power here on x is going to be, this is going to be x to the 12th. This is going to be x to the 11th. All right? Now, if this is 12, that has to be 0. If this is 11, that has to be 1, right? Because these have to add to 12. They've got to add to 12. So what is x cubed going to look like, right? That's what you and I are supposed to be able to figure out. What is x cubed going to look like? Well, x cubed is going to show up, right? When is x cubed going to show up? X cubed is going to show up when we have 2x to the third. Right? Isn't that when x cubed is going to show up? Well, if my power on this person here is 3, my power on this factor, right? My power on this factor, these have to add to what? What do they have to add to? Yeah, 12. So the power on this is going to be 9. Now, once I know the power on this is going to be 9, then that tells me who goes here. Remember, we pointed this out up here with all these red arrows. This has to match this. So they want us to work backwards. That's what they want. They want us to work backwards to figure this out. They don't want us to write the whole thing down. In fact, if we write the whole thing down, they're probably going to mark it wrong. So these questions, which there are numerous ones of these in the homework, these questions require us to analyze, think about, plan out, where does this term come from? Now, we can do the arithmetic. All of us can do this. All of us know exactly what this is. We know this is 12 factorial. 9 factorial, 12 minus 9 factorial. This is 2 cubed from Algebra 1, that's 2 cubed x cubed, And then 1 to the 9th is just 1. And we can all simplify this. I showed you the trick twice. 9 factorial into 12 factorial. That leaves me 12 times 11 times 10. Because 9, 8, 7, 6, 5, 4, 3, 2, 1. Those are all gone. What's 12 minus 9? That's 3 times 2 times 1. What's 2 cubed? You're right. That's 8. And we have x cubed. 3 times 2 is 6. 6 into 12 leads to 2. So what do we have now? 22. 22 times 80. That's what we have here. 22 times 80. And that's x cubed. So we take 22 times 80, right? We know how to do that. 22 times 80, we get 0, that's a 6. That's 1760. X cubed. And remember, the question said, what is coefficient? The tricky part is laying it out so we can jump down here without having to do the counting. We have to be able to do that. All right, so I'm going to do another one of these because, you know, your one's not enough. There's examples in your book. There are more examples online from other videos, and I'm going to do a second one right here because this is the question that most often appears on these exams in a pre-calculus level course. So let's clean this off. And let's do another one of those. Okay, another problem just like that one. And we'll pick a little trickier one. So they give us this now. X minus 1 over x squared to the 9th. And they want the coefficient of x to the 0. All right? Now, before we can begin to do this, we have to do some strategies. We got to bring in some strategy. We got to think this through. This is x minus x to the negative 2 all to the left. So what is our first, if we were to expand this, our first term is going to be 9, choose 0. 9, choose 0. This to the 9th. X to the negative 2 to the 0. What's my next term going to be? 9, choose 1. 9, choose 1. X, that's going to have an 8 on it now, isn't it? It's going to go down by 1. But what's going to happen to x to the negative 2? Well, this is going to be x to the negative 2 to the first. What's going to be our power on x right here? Isn't our power on x going to be 6? What's our power on x over here going to be? This is to the 0, so that goes away. Our power on x over here is going to be 9. What's our power on x over here? Think this through. This is x to the 8th. That's x to the negative 2. So I subtract 2. Our power on x is 8 minus 2. That's 6. 8 minus 2 is 6. What's the next one going to be? It's going to be 9 choose 2, isn't it? 9 choose 2. X is going to be to the 7th, isn't it? X, right? X to the negative 2 is going to be to the first. second power, isn't it? Second power. So what is this going to look like? This is going to be x to the 7. That's going to be x to the negative 4. We're going to get x cubed here. So our powers on x went from 9 to 6 to 3. They're not going down by 1. Like up here for this problem, they went down by 1 because there was no tricky x in our second spot. But now we have an x in our second spot. So now we pretty much got to figure it out. This next person right here is the one we want, isn't it? 9, 6, 3. This is going to be x to the 0. So who is this going to be? It's going to be 9, choose 3. This x, right? This x, we go down. 9, 8, 7. This is going to be 6. It's going to be x to the negative 2 cubed. So that's going to be x to the 6th. That's going to be x to the negative 6. That's going to be our x to the 0. This is the term we want. See, we want to do this analysis at the beginning. So what's our coefficient? That's what the question is. What's our coefficient? Our coefficient is 9, choose 3. So we have 9 factorial over 3 factorial, 6 factorial. Now remember, we picked the biggest one and cancel up here. That gives us 9 times 8 times 7, because 6, 5, 4, 3, 2, 1 is all gone. 3 times 2 times 1. Well, 3 goes into 9, leaves me a 3. 2 goes into 8, leaves me a 4. Right? So what do we get? We get 12 times 7. Right? 12 times 7, 84. All right. So there you go. This is what we're going to use, right, as our lesson on the binomial theorem. You can watch this as many times as you want. Watching it once may not be enough. Maybe you have to rewind and watch certain parts more than one time. There's nothing wrong with that. Read your book, watch this video or other videos, and when you feel ready, then attack your homework problems. Fine. Everybody have a wonderful day.